When we learned about horizontal asymptotes, we learned that when the power of the numerator is greater than the power of the denominator, then there is no horizontal asymptote, because the higher degree of the numerator overpowers the smaller one of the denominator. And therefore, when x goes to infinity, so as x gets larger and larger, then the numerator gets larger faster than the denominator gets larger. So it overpowers it, and it goes to infinity. Or it just keeps getting larger and larger, and the denominator cannot keep up with the increasing values of the numerator. But what we're about to learn right now is a special case of that. When the power of the numerator is greater than the denominator, but only by 1. And when that happens, we get something called an oblique asymptote. We don't get a horizontal asymptote, we get an oblique asymptote, which means we get a diagonal asymptote. So instead of getting a horizontal one, we get a diagonal one. And the reason for that is, say we have some function. What we're doing in a rational function is essentially dividing one polynomial function into another polynomial function. So when we divide a function, let's say if we were just to go through with that division, we would get a quotient. If it divided evenly, that's all we would get. But if it did not divide evenly, which it doesn't most of the time, that's why we have a rational function, then we get a remainder still being divided by the denominator. Now when we have the case we're talking about, when n is equal to m plus 1, when the degree of this numerator is greater than the denominator by only 1. So if we have a case where we have, let's say the leading term is x cubed divided by x squared. If they divided evenly, we would get a linear function in x. And if we had a x to the 5th, then we'd be doing an x to the 4th, and we would still get an x. So you can see where we are going with this. When we divide something that's one power less, what we're going to do is get a linear function, always. But if it does not divide evenly, then we're going to get a remainder. But what that remainder is going to be is a constant. So let's assume that this f of x, that n is equal to m plus 1, that the power of the numerator is greater by 1. So what we're going to get is we're going to get some linear function plus some constant divided by the denominator still. But bringing this back to asymptotes, when we were talking about horizontal asymptotes, we wanted to know what happened as x went to infinity. And this is the same here. We want to know what happens when x goes to infinity. When x goes to infinity, when we have this situation, it's going to look more, the function value is essentially a line. It just so happens that it does not divide evenly. So when we have a rational function where the power is greater than 1, as you can see over here, essentially this is a line. It just does not divide evenly, so it's in this form right here. But so as we go to infinity, it's going to look more and more like a line. But it won't quite be a line because we have this remainder. It's not that it's not a line, but it won't be this perfect line right here. And the reason it won't be this perfect line is because this remainder exists. However, as x goes to infinity, this remainder becomes less and less significant because we have a constant being divided by some function of x. So we have an x in there. So x is going to keep getting larger and larger. This constant is going to be the same. So this is going to go to 0. And we are going to be left with this line. So this line is going to be what the values of x approach. Because this is the same as this, but it just has this remainder. But as we said, as x goes to infinity, that remainder becomes less and less important. It will never quite be this value because of this remainder. It will always be a tiny bit more or a tiny bit less. So if we thought about, let's say if we had an x value of 1 trillion, and this c was a 1, then this would be 1 trillionth, plus whatever this is. So this value, while this would continue gaining in numerical value, this would be getting smaller in numerical value. So it will get closer and closer to this exact value, but it won't be this exact value because there'll be this infinitesimally small value being added or subtracted to it. So that's why we say that there's a diagonal asymptote or an oblique asymptote. And this will be much clearer in an example. So let's do that. Let's say I have f of x is equal to x squared minus 4 over x plus 1. And let's just say I want to graph this. We'll do the other steps very quickly and try to get to the asymptotes. So first off, we need to know what our x-intercepts are and our y-intercepts are. The x-intercepts are when the numerator is equal to 0. So we want to know when x squared minus 4 is equal to 0. We can simplify this by factoring it. We can see that the intercepts of x are going to equal minus 2 and 2. So that was simple enough. Now for our y-intercept, all we have to do is find the function value of 0. So f of 0 is equal to 0 squared minus 4 over 0 plus 1. This is going to be equal to minus 4. So the intercept of y is equal to minus 4. That was simple enough. Now let's quickly look for the vertical asymptotes. The vertical asymptotes are when our denominator is equal to 0, assuming that it's not divided out in the numerator, in which case it would be a whole. But we can see that over here we found out this factored was x minus 2 and x plus 2, so we don't have to worry about that. So what makes this equal to 0? Well, minus 1. So we have a vertical asymptote of minus 1. Now we ordinarily would look for horizontal asymptotes, but as we learned in our rules earlier, if the power of the numerator is greater than the power of the denominator, then there is no horizontal asymptote. However, we just learned about these new oblique asymptotes, and we learned that although the power is greater than the denominator, that means that this equation essentially is a line. It just does not divide out evenly, but it is a line. So what we're going to do is we're going to divide x plus 1 into x squared, and we're going to find out what line that this approaches. What line does this look like as x goes to infinity? So the first thing we can do is either use long division or synthetic division. I'm just going to use synthetic division because it's much faster. So we have minus 1, and then we have a 1, and then we have 0 for x to the first power. Minus 4. So we have a remainder of minus 3. So what we've just done is said that this function x squared minus 4 over x plus 1 is the same thing. If we divide this out, it's the same thing as x minus 1 minus 3 over x plus 1. So essentially what this function is x minus 1 but we have this remainder of 3 still divided by x plus 1. But when we're looking for asymptotes, we want to know what the function behaves like as x goes to infinity. And as x goes to infinity, we can see here that this example, it's very easy to see that as x gets larger and larger, what's going to be more important is this right here. Because as x goes to infinity, this is going to get smaller and smaller and smaller until it's practically non-existent. So we can say that this goes to 0 as x goes to infinity. This becomes closer and closer to 0. So therefore, that this function, as it approaches infinity, we get larger and larger x values, it's going to look more and more like x minus 1. When we have small x values, then this is going to have a large effect. If x was equal to 0, then this value right here would be equal to minus 3, which is large. It's actually the more important part of the function at that point. But as we move farther and farther away down the x-axis, this becomes almost completely insignificant. At x is equal to 1,000,000, this would be practically nothing. So we found our oblique asymptote, which is equal to this. And now we can make our chart. But before I fill in the chart, I want to point a few things out about oblique asymptotes. And normally, they are, while most people think of them as more difficult, well, actually, let's make the chart first. So we had intercepts of -2 and 2, and we had a vertical asymptote of -1. So -2, -1, 2, and this is a intercept, and this is a vertical asymptote, and this is an intercept. But what I was going to say is that normally oblique asymptotes are going to be much easier to graph. And I know most people think that they are more difficult because it's a diagonal line and therefore it should be more complicated. But as you're going to see, often it reduces the amount of work we would have to do if we think about it a little bit. So let me make the graph first and explain what I'm talking about. So first, let's put the asymptotes that we know and the zeros. So we have a vertical asymptote at -1. Next, we're going to introduce our new type of asymptote, our oblique asymptote, which has an equation of x minus 1. We can put that on the graph here easily enough. We can use just x-y intercepts when x is equal to 0, y is equal to -1, x is equal to 0, y is equal to -1. And when y is equal to 0, x is equal to +1. So there's going to be an asymptote going through these points. So this is the line that the function is going to approach diagonally. And now what we have to put on our zeros, -2 and 2. Here's -2 and here's 2. And what I mean by being able to avoid work is if we look at the graph, here we can eliminate almost all of the work because this is a 0 So that means the function must pass through this point and approach this line and approach this line. And it's not going to be possible for this function to be down here somewhere because it can't cross through this asymptote. So therefore, this graph must look like this somehow. And same thing for this. We know that this function can't be up here because if it was, there would be no way for it to get to this 0. And some people might not be able to see that intuitively. This kind of, I guess, intuition comes from just understanding that this function is essentially a line. It's just not a line that can be divided evenly. So it's not going to have all kinds of crazy shapes where it just changes direction all the time because it's going to act like a line. And the only reason it changes direction is because of these asymptotes. And it doesn't even change direction, it bends the line that would otherwise be straight. So if we know where the graph of this line is going to be, it makes the chart not really important, or we don't really need to do anything. Like for this part of the graph already, we know that the y-intercept, let's go back up, the y-intercept was equal to -4, I think. Yeah, the y-intercept, so x is equal to 0, x is equal to -4. X is equal to 0, x is equal to -1, 1, 2, 3, 4. So I can already make a graph that looks something like this. Well, not quite like that, but it would look like this. So it would approach that line, and then it would approach this horizontal asymptote. So I'd be able to graph something really rough like that, if I wanted to. Or we could do the chart. I'll just do the chart anyways, because I understand that a lot of people aren't comfortable with math that much, and they just want to just do something that's very steady and will give you the correct answer every time. But what I really wanted to take the time aside to do is to point out that if you can see a shortcut, don't be second guessing yourself about that shortcut. Go ahead and take that risk and calculate it, and if it looks right, it probably is. Because a lot of times in these books that you're going to be learning about, they don't really have time to explain every shortcut or you kind of have to discover them on your own. And no one's really just going to walk up and tell you. So if you are just doing problems and you are experimenting, go ahead and try and see if it works. And if it looks like it should work, should probably... The other thing is, a lot of problems in the future, it's going to require, not right now, but I'm trying to prepare you for math very, very far in the future, where intuition will be able to save you a lot of work. In a case like this, where it would be able to save you some work, because we could see where these are going. But anyways, let's get back to actually doing the chart and figuring it out this way. So one point we can select is -3. And let's put our equation over here, x squared minus 4 over x plus 1. So we put in -3, it's -3 squared minus 4, -3 plus 1. So this will be 9. 9 minus 4, that's 5, plus 2, so that's -5 over 2. So it's going to be negative here. But as you can see, it's just not that useful. So we already knew that it was going to be right around here somewhere. It couldn't be anywhere else. So we tried what's this, -2, so we tried -3 and then -5 over 2. So that's going to be 1, 2, and then a little bit below, so it's right here. So we're already kind of expecting something like this, and then it's going to get close to this asymptote. And next we need to test a point between -2 and 1, but if we look at our graph, we know it's going to be somewhere in between here and the asymptote. We know it's going to come up and approach this asymptote. So it makes the chart kind of a waste of time. But it gives us a more accurate graph if we get a point rather than just drawing some random line. So let's just pick something. Let's pick minus 3 over 2, so minus 1.5. So we have minus 3 over 2 squared plus minus 4. Minus 4 minus 3 over 2 plus 1. So this gives us 9 over 4 minus 4. That'll be minus 7 over 4, and then divided by minus 1/2. So that'll be 7 over 2. And positive, and we already knew that it was going to be somewhere over here. So this is around 3 something. So it was here, 3 something, 3.5. And this is kind of what we were expecting, just from the location of the 0. So the location of that 0 told us a lot. We already knew that it was going to have to come down this way somehow, and it was going to have to go up towards the asymptote somehow. So that's what I mean, that we were able to, by just looking at where the zeros are, we're already able to figure out what the graph was going to mainly tell us, and we could just pick points and just plot them. Next, we wanted a point between minus 1 and 2. We already picked 0 for the y-intercept. We had f of 0, and it was equal to minus 4. So we don't need to do that. We already have that point down there. Lastly, we need to pick one between 2 and infinity. So let's just pick 3. We have 3 squared minus 4 over 3 plus 1, and this is going to give us 5 over 4. We have 5 over 4, so it's going to be here somewhere. Maybe a little bit lower. Just not very good at drawing. But anyways, it looks something like that. Not Leonardo da Vinci, never claimed to be, never was, never will be, but there you have an oblique asymptote. And like I said, these can be, a lot of work can be saved just by thinking about what you are graphing, or just thinking about what you're trying to do, in just any situation. But anyways, this is more about oblique asymptotes. So there you have it. It's a diagonal line. When we're looking for oblique asymptotes, we're essentially looking for a situation where the power of the numerator is greater than the power of the denominator by 1. If we can see that, we just divide out, we find what that equation of the linear function is, or the line, and then that is our oblique asymptote.